computer. Yeah, now we start recording. And now we stop sharing. And go to our book. And we open it somewhere. File. Book complex analysis. Conjugate. Chapter complex numbers, and we go what we approached. We approached quite long. We integrated functions over closed contours, and we were able to calculate. Yeah, so this is more or less. We go through maybe main formulas once again. Function is analytic. If and only if integral over any closed contour is 0. How we prove this? We prove this by how we proved. Now, okay, we arrived to pole singularity. This was more or less as, for example, this is clear that this is the pole of degree. No, we need not to check these conditions, removable and non-removable singularities. We go now to integration. First order simple pole. Yes, this is residue. But as we told, we need not to write in this way. We need not to write precisely in this way z minus 0 fz. But we can just extract this z minus z0 in denominator. Extract this in the denominator, and the rest will give us residue. Did we share this? We did not share this. Yes, we did not share this. Share. Now we go back. We are here. Yeah. Now we share screen. I'm sorry. Yeah. So we share screen. Simple pole, residue at the pole, selected functions with the pole, 1 over z. Yeah, so this function, so this in denominator z cubed, and this is non-zero in the point 0. So this is the pole of the degree 3. Yeah. For example, how we work with sinuses and so on. If you interested, for example, in the pole, there is quite long, in the book is quite long story how to understand the pole when there is some elementary function and some denominator. For example, if we have cosinus or beta sinus z divided by zm. Do as you did in usual analysis. A bit later, we shall see that all these functions have their Taylor expansions. So it will be just maybe even today that functions of complex variables, they can be expanded in Taylor series. And you know Taylor series for sinus z. Its first term is z. So you can tell that when z is going to 0, this can be represented z divided by zm, so it is zm minus 1. So this is pole of degree m minus 1. And it can be more complex. There can be exponents and so on. You can also, for example, it can be exponent z minus 1 divided by z squared. Of course, you can multiply, take limits and so on, but you expand the exponent, you get approximately 1 plus z minus z divided by z squared, and it is 1 over z. So this is simple pole of degree 1. So this, of course, you can use this, I can say, abstract definition with limit, but this is typically much easier to do in this way. So all elementary functions of complex variable can be expanded in Taylor series, And these Taylor series are the same as was for real variable. And it is clear why, because on the real line, our complex analysis is coincide with your previous real analysis. So we cannot get something new because on the real line everything is the same. On the real line, everything is the same. Yeah, so these are poles. Then we started to integrate. And we derived somewhere this is very standard trick which will be used everywhere, that if you get integrals, this maybe a bit, yeah. So if one integral go up and another go down, up and down, so this is zero, So if you have two which are goes in opposite directions, then it is zero. Integrals which we calculate typically counterclockwise. To get integral clockwise, you will take just minus. So direction is just minus. Yeah, okay. And what formula was finally derived at the very end of last lecture? This formula is very important. What is maybe disturbing me? I'm not sure, but it seems that you could not use the books during examination, or can. What is your experience before? Can students use the books, or it's forbidden? No, because my idea was that maybe you need not memorize proofs, but on the other hand, if you cannot use books, you should memorize.
Because they different for different courses. Some they allow us to have one handwritten note. Some others they have a formula sheet, and some they
So
don't
in
have.
principle, I can tell you, you can use just the book. Yeah. Good. No, because the main idea is not to memorize the proof. My question would be not write me the proof of this theorem. My question would be why this follow from this.
But how does it work if we have an electronic?
Oof. Then you can use mobiles is not good to use that. Then you can have clever friend who can help you. Okay, I shall think about this. No, because typically what is happen? Students memorize all proofs, and in half of year you have no idea what this proof was. Proofs you forget practically immediately. No, I shall ask my colleagues how they do this. The problem is that before I had only advanced courses, and here students have only oral examination. When we sit near each other, he has the book, and I can tell you why this follow from this, or how this connected with this, and it works very well. If somebody no proof, he can explain. If somebody just first time see it, he cannot explain. But yeah, we shall solve this problem, no problem. Так, we go to our main formula, and this is maybe you even can write somewhere this formula that should be in your brain. Not so many, but maybe I will make the sheet of formula, the list of formulas. So the formula is 385. Such integral over counterclockwise. CC is counterclockwise, so this is in this direction of analytical function of function which has singularity. Which has singularity in the point z0 is equal to pi I residue in this point. So if function has just one pole, and the point 0, this formula. If you go as another direction, clockwise, it is minus. So you should maybe automatically understand, because maybe some problem will be, I write you the counter, not counterclockwise, but clockwise. Then you cannot use this formula with plus. Then you should use this formula with minus. So it is important to understand. So now, for example, we considered this example. So this function and Z0 is 2I. Case in numerator there is, it's not 0 in this point, yeah? So this is singularity, this is pole of degree 1. So we can take it away and calculate residue. So we forgot about this, and put just our 2I in this function, 2pi. And now put in this function, it is exponent 2I. And sinus, we studied somewhere, and it is also good to remember that we studied such things. That if we take sinus I z, it is hyperbolic. It is hyperbolic sinus. It is hyperbolic sinus. How it writes? So, okay, of z.
It's times I.
Yeah, somewhere is I. Yeah. Up to constant. Up to constant. Where is I? Here or
It's I in front. You multiply
Here,
sine h z with I.
yeah, okay. So this formula, send it, this is even not up to constant, it's with this I. With this I. Okay, so how this would be one of the standard problems for you. Some function with pole, typically of first order, and calculate the integral. Sometimes it will be two poles, and now we go to situation when function has two poles. Cauchy residue theorem. So this is what you should have from this course. We would not ask you to have everything in, but for example, Cauchy-Riemann condition. This should be in your brain. Then it should be the integral of a closed contour of analytical function. It is 0. It is 0. Then you should know Cauchy formula. That we take integral of function which has pole of degree 1. It is 2 pi I residue in this pole. And such basic formulas should be in your brain. Should be in your brain. More than one pole. Okay. We did more or less the same. As I told, this is typical of what people do in applied science. They see that the function has singularity. Of course, in reality, you don't have singularity. The electrical charge cannot be infinity. But in ideal model, when electrical charge is in the point, electrical charge is never in the point. It is on some ball. So it would be, for example, high electrical charge, but not infinity. But in mathematical model, it's good to describe it 1 over z, yeah? So they take these 2 points where our function go to infinity and go to infinity as 1 z minus z0, make circles around, and then integral is reduced to integrals to circles on these 2 circles. And we again repeat these long calculations, and then we can parameterize circles. So the main idea is that we can have around, for example, we have some contour, very complex contour, and here 2, for example, or one singular point. To parameterize and calculate integral over this complex contour is very difficult. But then we take 2 small circles, and then, yeah. Since here our function is analytic, integral is 0, So we put direction counterclockwise, and then we can put θ typically direction other way around. No, to get minus, because we would like to have that this is equal to this. So then we should, to go to another side of equality, we should have minus, so we here put this. Yeah, good, good. They have this picture, and then over circles, integrate is very easy. This is also to good have this in your mind, this parameterization of a circle in the center in the point z0. So parameterization is simple, z0 plus, and this is unit circle of radius rho. So, and then you put the integral, you integrate, and you get another Cauchy formula. So integral counterclockwise of function which have two poles in the point z0 and then 0 prime is 2pi, residue in this pole plus residue in this pole. And immediately by taking many points, taking away many points, we can get the same formula. We can get the same formula for n simple poles. So this is still more or less our function. Our function is of this form for this picture. For this picture, maybe I take another. It's not a good color. Not a good color. This picture corresponds to functions which are such. Z minus, for example, Z1, here is F1Z analytic function plus, say, maybe even not plus, but it can be even product, Z minus Z2, and so on, Z minus Zn. And for example, here this function is already without singularity, and we want to integrate this over this contour. Of course, typically it's not written in this form. No, typically it can be written in this form. Sinus z divided by z in the degree m plus 1. Then you should first find roots zk. This is the root. This is the root of the degree m of 1. And we did this at the beginning of lecture. So you find all this zk, and then we can expand in this way. And then you can integrate by calculating residues. For example, how calculate residue in this pole? We just forget about this and put in this function z1. How calculate residue in this pole? Now we forget about this and put z2 in the rest, and then take 2pi and the sum of these residues. So very automatically you can do this. You can do this. Yeah. If you go clockwise, just to disturb your mind, I can write your integral with the arrow clockwise. It would be minus. It would be minus. They precisely considered this example with two poles, and we need not consider this formula. This formula. It is not only for circles; it's for any contour. For any contour, yeah. And let us destroy everything that we wrote. Everything that we wrote. And now, for example, this function. And they do precisely as I told. They found two square roots of minus 1, I and minus I, and then depending on how many singularities are inside the contour, we apply either here it's for two poles, here is only one pole, and here is only two, the second pole. Which is interesting in physics, in some way, physicists with their intuition, very often, as I told, they go, you see, for example, here is singularity, and you should go, for example, over and so. But you have another way, you can so and so. And physicists know what way to go, because mathematically it's more or less the same. But, for example, typically they go this way. And if it go this way, you will get non-physical solution. So physics is not precisely mathematics. They should have intuition that your answer in mathematics, all answers have equal rights. You make calculation. If you did not make mistake, you get right answer. But physicists should have intuition whether this answer has physical meaning or not. I spoke with them many times. I never got to know how they do this. Do in some way, yeah. So sometimes mathematicians think that we are much more smart than engineers or physicists. It's not correct. It's not correct. We may be more smart in calculations and proofs, but typically people who do applications, they have more intuition. But intuition is unexplainable. We cannot explain intuition. I think it maybe never. Yeah, so they calculate in both poles this upper integral, this integral. Yeah. No, yeah, so this is now this is new material. In fact, before we just more or less repeated previous two lectures, and now new material for higher order poles. For example, if here we have not first degree, but for example cube and so on. Yeah, so this is more complicated situation. This is more complicated situation. So consider we have some analytic function, but let us consider this function. So this is we just produce singularity, or we can go other way around. We have function f with singularity with pole of the degree 1 in the point z, and then we extract analytic part and this pole in denominator, one simple pole. We apply Cauchy residual class residual theorem. So we write this integral. So in this, how we get residual? We should multiply this function by w minus z and take the limit. So this is this, so this is this answer. So we got such formula. Which is called typically Cauchy formula. And this is also one of the main formulas of this course. So this is one of the main formulas of this course, which we got with very simple trick. So we just, instead integrating just analytic function, we integrated this function divided by this singularity block. So this block precisely produces singularity. So I suggest you to have it in mind, and also have in mind how we prove it. The proof is very simple. We know that if we have a function with pole, then this integral is equal to residual. But if our function is of this form, residual is precisely the value of function in this point. So this is the proof, where is our formula by itself. So the idea is that residual of this function is precisely value of this function. No, up to 2pi. Okay, so this formula will be our main machinery during the lecture. Yeah. Now, where this formula is correct. Its formula is analytic. One remark. So if this function, where this formula is correct, for which go up to this formula, where this formula is correct. Here is integration around z. So, and this function have the pole in the point, this function has the pole in the point z, but maybe it has also some other pole, for example, u, or some singularity. So this contour can be everywhere beside this singularity. So this representation is valid in any area where this function has no singularity. So for example, if this function f z has such, for example, z minus 2, z minus 2. And here is some function, any complex function, for example, any analytic function g, or for example, cosine of z. Okay, any complex function gz. Then where this formula would work, for which z? It would work everywhere up to this point 2. So we can take this formula is correct everywhere up to very small neighborhood around 2. So when you apply this formula, you can do this up to you approach singularity. You can make this larger and larger. But if in this point our function f has singularity, you could not go to this point. So this formula is valid everywhere where this function has no singularity. Then we can, now we make break maybe just in 1 minute. Then we can differentiate this formula, take derivative of this formula. So you see that z is parameter, and if we differentiate with respect to z. So we get this formula. Minus go from here and minus go from denominator. And in this way, we can calculate all derivatives. Of our function. And finally, we get this formula. This formula, you need not to memorize this formula. You can derive it from this Cauchy formula that we wrote above. So this formula we need not memorize, but you should be able to get it because it is very useful. And now I suggest break, maybe not so long. For example, now it's up to 11:10, 7 minutes break, yeah? To 11:10. And then we continue.
Jag och fysiken. Besvar med nästa fråga nedan. Båda bägge lösningarna. Ja.
Jaha, okej. Men så
Jag bara frågade i alla råvaror på min form som får format.
första båda okej. Båda lösningarna.
Jaha, det vet jag inte.
Du ska svara på det.
Ja, men det måste ju inte jag nu.
Nej, men alltså, du kommer svara om det. Tänk efter nu, potentialen. Den var ju en halv m omega kvadrat, så x kvadrat.
Men det gör
Så vad kan man säga om potentialen? Potentialen var ju jag kan skriva
en halv en omega kvadrat. Ja. Men då måste den vara
x kvadrat med. Ja, exakt. Den är ju
den är alltså 0.
ja. Och den totala energi, det är ju potentialen plus den kinesiska energin. Och han sa ju på det att den kinesiska är ju alltid större lika med 0 på grund av v-kvadrat.
Ja. Men då kan ju potentialen vara mindre än 0.
Nej, men vi visste här att den kan inte vara mindre än 0. För x, det är x i kvadrat.
Ja. Jo, precis.
Så det är större lika med 0. Så båda ja, men så de vet att den totala energin är större lika med 0.
Ja.
Så om den innehåller bla 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 gånger a som är plus minus. Då måste A och E båda vara bara positiva. Så där har du så.
Är det ändå bra?
Det är lite häftigt det som står i...
Och det är det så nu. Det där med att använda bara det som funkar.
Men har du läst om Heisenbergs osäkerhetsprincip?
Nej, jag har inte läst den. Men det ska finnas i första och andra kapitlet. Men vi hoppar över då för mycket.
Ja, det är kapitel 2.
Alltså, vi ska läsa de sidorna nu.
Ja, det är typ 4 sidor.
Okej, bra. För jag får inte varför jag ska skippa den. För det är så
Det är typ 4 sidor. Det som är så häftigt är att en partikel kan inte vara stilla. Den kan inte ha noll i kinetisk energi.
Jag kommer ihåg det från när jag gör så blir det här blå utan när han säger ja men vad är det ifall han säger noll då? Det är där med det bredvid. Han bara det går inte.
Det går inte.
Och vad tror du?
Nej,
Det är ändå ganska coolt.
det är ganska coolt. Sen var det ingenting om hur den här osäkerhetsprincipen kom till. Var typ, om du har tillräckligt stor yta så kan du med någorlunda säkert bestämma en position.
Men inte
Och
exakt.
hastighet. Men ju mindre du gör den, desto mer, det är typ, ser det som att ha en kula som går fram och tillbaka. Ju mer du trycker ihop den, desto hårdare man hoppar fram och tillbaka. Fram och tillbaka. Samma sak gäller för partiklar. Om du har tillräckligt liten plats så kommer det till slut vara så pass lite så du har ingen aning om vad de befinner sig i. Och det är det som är osäkerhetsprincipen.
Så han tyckte
Eller obestämbarhetskritik, de kallar det.
Heisenbergs osäkerhet. Så säger jag. Osäkerhet.
Obestämbarhet, någonting är det i boken.
Ja, men jag vet det bara från gymnasiet och jag har ganska svag osäkerhetsrelation.
Ja, osäkerhetsprincip är det Staffan sa.
Och Staffan är också elektrostatisk istället för elektromagnetisk. Eller elektrisk kraft nu, inte elektrostatisk.
Formen för den nästan utan till. Jag minns vad det är
2 minuter.
Ja, fan kan inte in.
Men han sa, ja det är det. Så jag löste den till 75%.
Vad frågar du inte om jag förresten? Nej, inte.
Men
har ni kört
lösningen? Den var ju helt
Jo, jag har gjort uppgifterna. Jag gjorde igår hemma. Integral, alltså 2.2. Jag kunde inte första. Du kan man ju lång så jag tar produktionen.
Så jag tänkte okej, jag ska få en ny material och försöka göra någonting så jag lyckades på
Men det är liksom kan köra någonstans.
Sen hur
Vad sa du? Du kan...
Alltså, flytta upp.
Så han fick hjälpa mig väldigt mycket med det.
Så jag gillar dem.
Och...
Nej men du jobbade på onsdag, eller var det någon onsdag?
Nej, jag hade ju det, men det var...
Men efter att han sa att
Jag tog efter. Jag köpte syven vid 13 när jag kom tillbaka sen så gick jag på gamla.
Men så han ville veta
Man kollar upp alla man har alltså sådär.
Han utnyttjar det faktumet att man kan se om det är lite vit och saker.
Var det något efter lektionen?
Om jag har något efter den här lektionen.
Ja.
Jag tror, nej jag har inte det faktiskt.
Jag köpte syven. Jag ska prata lite om syven, men efter det så är jag på pluggen.
Jo, exakt.
Man vill också med.
Då var det att kolla om de var... Du behöver inte memorera bevis.
Men sån här boken, det har jag aldrig hört förut. Det var en gång ute i högstadiet, det var historia.
Eller nej, det var en.
Och det var ett undantag, varför var det, jag vet inte varför. Det var en styck värst.
Vi har ju sådana som har musikbok i teknik.
Ja, lite annat har jag hört. Men bok har jag aldrig sett.
Räknar också.
Jag har aldrig hört det. Ska vi säga det vanligare med bara formblad eller formbok? Ska vi säga till om det är alltså det är mer vanligt, alltså det är vanligare med formbok eller formblad.
Jo, det skulle vara form eller blad liksom, eller att man har form.
Jo.
B på pappret. Men han fick bara en...
Våra kommententan bara vara bevis och så.
Nej, alltså jag tror det kan vara bara computation. Sen så kommer det vara lite så lite...
Kanske för VG eller något, eller du vet, A kanske.
Jo, det kommer ju vara... Jag tror att det är lite så... Man delar upp det en bevisdel och en computation.
Ja, jag hoppas inte det är som jag tyckte också när man måste ha det. Teoridel, utan jag undrar ifall du som är migrant, att vet, några räknar och så du kan inte få bevisa om man vill.
Alltså, det finns ju teoretiskt. Så
Ja,
det ska ju
fast-
kunna bevisa.
Ja, men inte...
Ja.
Vi ska kunna använda resultat.
Det är dock två olika
För du
kunskaper.
vet, hålla på och dribbla på teori.
Ni ska ju också hitta på egna saker och sånt för att ni ska kunna bevisa saker.
Men fysik bara inte helt samma.
Nej, det är
Men jag förstår vad du menar. Du gör det måste han försvinna.
Han måste ju kunna.
Jag vet inte vilka... Ja, men det var för att man skulle ha på balansiert och då har brukat som det var mycket kvar. Det är rätt bra för.
Ja, det verkar bra.
Alltså det finns
Alltså vi har insläppare varje vecka på väg. Och sen ska vi avsluta upp med
Nej, men det känns som
vilket jag bara och jag är jättedålig på att
En sida. Jag såg det
och så kanske
det var liksom en sak. Vi var förspelade för att sen har vi en så den är liksom och sen har vi datorn ska vara i slutet på kurvan. Det är ju man behöver ha rätt mycket förkunskaper på det.
During the break, I got a very strong voice of mathematical student, which was a kind of protest, because in mathematics, typically how we do, we write theorem, formulate theorem, then we write proof, and we write the proof. Here, this book and this course goes other way around. Typically, first they present how they obtain some formula, and then write formula. Of course, it can be reformulated as theorems, but you start other way around. This final formula is formulation of theorem, but what was before it is its proof. So, for example, go back to this Cauchy formula. How it would look in the book of mathematician. In the book of mathematician, Cauchy, it would be called theorem Cauchy integral representation. It will be written this theorem. It would be written this theorem as theorem. This formula valid for any analytical function f to v, and then proof, and proof would be this one. Take this function, write this formula, and you get fz equal to this or this divided by 2pi. So in principle, if you're more mathematical soul, you can reformulate everything. For example, if you go to poles, integrals for function with two poles, how it would look in mathematical book? In mathematical book, it would look in this way. For example, for 2. For any function f which has poles of the first order in the point z0 and z0 prime, this formula is valid. Then you write proof, and you go up to the beginning of these considerations, and this is proof, and this is proof, Oh, this is proof of this up to now of this formula. After this, you write corollary that this formula can be immediately generalized for n poles. No, this is the problem that this course for both engineers and mathematicians, but I think it's not problem just with this remark. The final results, you formulate a theorem and everything what was before is a proof. I see that mathematicians are not so happy, but it's not easy to make happy at the same time engineer and mathematician. I don't know how to do this, that both be happy. It's very big difference. Okay, in any event, we get this formula. After this, as engineers, we start just differentiate this formula with respect to z, and we get this formula, final formula for derivative. As mathematician, you can write this formula and tell that for any analytic function, for its derivatives, we have this formula, and previous you will write as proof, In any event, we have this, in any event, we have this, in any event, we have this formula. In any event, we have this formula. Now, what we have, then we can write this, we can write this, we can write this, and then this. So this is the formula how to calculate this integral. So it is more or less other way around. Yeah. So then they consider example. They consider example how to find this integral, how to find this integral, and how they do this. We should now apply this formula. So if you have this, then it is not just value of function in the point z0. For the if n is equal 1, it would be just no, n is equal 1 not good because it's n should be equal. If you have 0, n equals 0, so derivative of 0 order is just value of function in this point. Now we should find derivative of order n, and this is this integral. So this is, again, this is theorem. This is theorem, how to calculate such integrals, It is generalization of previous formula when n was 0, So now the difference is such, here is this degree, and here is n. So n is not precisely the same, but 1 degree less. So, and they consider example, which is more or less a very good example. Take the point 1, so this is this integral. This function is not 0 in this point 1, so it is only singularities here. So this is the pole of the degree, 3. If the pole has degree 3, go to the previous page. If here is 3, here is 2. And they do this. So they should take derivative of the degree 2 of nominator. So they take this derivative and they calculate this integral. So it's not so difficult, and it would be more or less also the problems for you. What is my idea? That you will get this individually, so everybody will have his own pole and his own degree, It can be done very simply. We shall explain this later. If there are more, it's not only one pole, but a few poles of degrees larger than 1. So, for example, this is this typical function, z minus z1, z minus z2, and z2 different poles. This is the pole of the degree m plus 1, and this is n plus 1. So, this function is analytic in the first pole. We take, this is more or less the same machinery. To work in this pole, this function, the rest is analytic. So this function is analytic at this pole, and this function is analytic in another pole. It's another pole. And we apply this formula, calculate derivative of function. For this is the first pole. It's analytic in the first pole, and this is analytic in the second pole. And then we take the sum. So this integral is equal to this. It just looks very big, but for example, m equal to 1, n equal to 2, it's not so difficult to calculate. So now we can calculate any such integral, and even more we can calculate any integral, and this would be more or less what you will get. Integral of this, for example, here is some function, maybe very complex, but analytic. And here would be, for example, z minus I square z plus 1 square, and contour would be, of course, contour could not go through point I, yeah, this is point I, this is point minus 1. So either you can get the contour which contains 2 poles, or some contour which contains only minus 1, which contains only 1 pole, for example, this contour. Or some contour which contain only this pole. So this is machinery for these integrals. Good. Yeah, so we go further. And it's again a theorem. It's again was theorem, yeah. With several poles, and they give example. No, they give example for concrete numbers. This is the pole. There are 3 poles in the point 1, 0, and 2. In 1 is pole of degree 2, in 0, 3, and in 2, 1. And we get this formula, and it's depending where is our contour. So the problems we will use not from this book, but from the book with exercises, but they are more or less similar. I think some of them are even the same. Now we go what I taught and what is more or less the main picture, what is analytic function. So our aim, now it would be our aim, this hour, to show this analytic function, if function is analytic around the point z0, this function can be represented in the form n from 0 to infinity. Here is some coefficients an, and here is z in degree n. So this is our aim, to show that it can be not zn, but z minus z0 n. So our aim would be now to prove that any analytic function can be expanded into Taylor series, and this Taylor series converges to our function. So more or less, the previous story was very long. We started with Cauchy-Riemann conditions, which were conditions to function of 2 variables. Cauchy-Riemann conditions. And in fact, Riemann became famous, but he was very bad teacher. He was so bad teacher that students never go to his lecture. And he was about to be fired from university, but what he did, it was in Germany, other teachers were so strict that when the bell rings, they closed the door. But Riemann left his door open, and all students who were late, they came to Riemann, and he had few very bad students who came half an hour late and so on. But finally, nobody knows the names of other teachers who were good teachers and who closed the door and so on. But remember the name of Riemann, and you know the Riemann, maybe we will come to Riemann zeta function. Maybe I give you talk. It's not in the program of the course, but it's good to give you talk about Riemann zeta function. It's complex function and so on. And to solve this problem, you get $1 million. 1 million. Maybe it's not the easiest way to earn $1 million. Yes, maybe you can easier to get $1 million than to solve Riemann problem. But okay, so this is our aim. Starting with Cauchy-Riemann conditions, we should approach this formula. Who will be the basis? Who will be the basis of this formula?
Sorry, Could you please just write there because it's a bit unclear for me to see.
But it's better for those who are inside because it's more or less very good. Yeah. Yeah. So
Understand.
yeah. Okay. So our way would be to approach this, and this is we are practically here. The main formula is here. This fz, which can be represented as integral fz, or fw minus z is z, and here is 1 to pi. So from this formula, now I follow recommendations, which maybe first you will give idea and then show the proof, which is, then idea is very simple. You have this function in denominator, 1 over w minus z. In the course of your usual analysis, you was able to expand it into power series with respect to z. So somewhere you remember that this function is w minus z in the degree minus 1. Did you consider it Cauchy? Did you consider it Taylor series for such function 1? Or let us, for example, this would be 1. Yeah, even simpler. If here is 1, this function you know. This is the sum of whom? This function 1 will divided 1 minus z. This is the sum of geometric progression. Yeah. So if you take sum n from 0 to infinity zn, and zn is less than 1, you get this. So more or less everything would be reduced to this formula. So the idea how we get from Cauchy-Riemann condition this expansion is following. From Cauchy-Riemann condition through green formula, we approach this formula. Then in this formula, we see this denominator. This denominator is up to W is this one. And then since we know how to expand geometric progression, we can get expansion of any analytic function. So this was how people arrived to this. So it can be theoretical question on exam. How you can approach, give me this schematic presentation, how you come from Cauchy-Riemann condition to this formula. Without proofs, without just follow this line of mine. The logical chain, how we approach this. Yeah. So now we destroyed this and we go, in fact, to proof of this formula. Now to be the proof of the, in mathematics, it should be formulated in this way. If function is analytic, it can be represented in this Taylor series, and these coefficients are given as they should be. Coefficients an is derivative of the degree n in the point z0 divided by n factorial. And then would be proof. But as the book is for engineers, first they will go from this integral formula and then they approach this formula. So they go other way around. Of course, it's more. Of course, it's heuristically more natural. Of course, I see the protests of mathematicians, but in mathematics, when I was students, this was typical, very strange. Suddenly, you get some formulation. This formula is correct, and then you start to prove. But first, mind where you get this formula. Engineers go, they first get this formula, and then you can formulate this is theorem. This is theorem. And mathematicians do always this. They first make some calculations and so on. They get something. Then they formulate this as theorem, and all your previous calculations they put as the proof. No, you do, if you do something, you do it this way. You never can from God get the formulation of some theorem. No, there was some Indian guy, I don't remember, Ramanujan, I think. He proved maybe 200 different formulas in number theory. Terribly complicated. And he typically told that he got from God precise formula. his formulas are very unexpected. So nobody could, he was maybe genius in number theory. Ramanujan, yeah, maybe I will give you his formulas to understand this. He was precisely as you want. He first got from God formula, and then he started to find the proof. So it was, but I'm not such guy. No, I cannot get nothing. God sent nothing. You should think and so Taylor series for analytic function. Okay, so we go. What we do? This is our point Z0. This Z0 which was on the table. Now we take some circle around it, take point Z, and the main parameter would be this distance from the center to this point Z, We get this integral, which we can represent in this way, It was not good that before was f small, now it is f large, but okay. There is this difference, the distance from our point Z to the center of the circle. Now we can write the previous formula in the same way. So the previous formula was this one, but now we write this double with respect to this. So we write in this way fz. We can write z as z0 plus this difference. Z0 just cancel each other. And we can write in this way. And now we want to see such circle where we have this. So, yeah. And then what we do more or less as I told, with geometric progression. So, but we have not, here is not one, but some number, we take it away, and we get this. So this delta divided by this plays the role of this parameter of geometric progression, of this number which was in geometric progression. So if this number, parameter t, is less than one, we can expand in geometric progression. So this what we have in our integral, and under this condition, we can use geometric progression. They told that in appendix there is derivation of this formula, but it's the same as for real numbers. Maybe you need not repeat this. For real numbers, you derive the sum of geometric progression, but here is everything the same, nothing different. So now we did this, so we expanded this. And now we put, instead of this, which was in integral, we put this series. Now, this very delicate point in this formula. Engineers do not pay attention. They typically change series and integral. And it's work always. To find example when it does not work, it's very difficult. But there exist counterexamples. Not always integral of series equal series of integral. Not always. There should be some conditions. We shall discuss them in the next lecture when we can change integral and series. Here they do this because before it was this series already changed. Integral should be here because we have this is equal to this, and it was under integral, but they changed, and now this term only in the integral. This delta, it does not depend on W, it is z minus z0. So we get this formula, And delta is what we wanted. Delta is precisely z minus z0. So we get this Taylor formula. They even write it's below. Yeah. So now this formula is theorem from a symmetrical viewpoint, we should do the following. Suppose our function fz is analytic. Is analytic in some neighborhood around z0. Around z0. Then this function can be represented as its Taylor series. Is a Taylor series, and what was before it is proved. It is proved. So this is one of the main results of complex analysis, which we can speak either about functions of two real variables, satisfying Cauchy-Riemann condition, or about functions which are represented by power series. So theory of analytical functions is in fact theory of power series. Of course, it does not converge everywhere for all functions. For example, for Ez, cosine of z, the same as was in your real analysis, sine of z. All these functions, they do not have singularity. So this series converges in the largest area, in the largest circle, which does not have singularities. So this series converges in the largest circle. So this is one of the main results of complex analysis. So everything is represented by power series. If z0 is equal to 0, then it is Maclaurin series. And now we're coming to the equation of convergence. So the value in the point is the same as the series. This everything is correct until our contour does not cross singularity. So it's better maybe consider some example. Consider some example. For example, consider function 1z or 1 minus z, where this function has singularities. Singularity is the point, say u equal to 1. So in the point 1, this function has singularity. But where we can expand this? In this circle which does not contain this point. So in this circle, z strictly less than 1, this series converges. So, and this is more or less illustration to general situation. If you have some function, arbitrary function, and if you have some point where we want to expand it, for example, some point z0, and we want to expand it into Taylor series, we should make the largest circle which does not contain singularity. So this function can contain singularity somewhere here, another function. Then we can take the largest circle around z0 up to this singularity. And here everything is good and analytic. But how can we do something if there is singularity? Can we expand our function if there is some singularity? Yeah. So we shall go to this. Yeah. Radius of convergence. Yeah, they make this picture. This is point z0, and here is singularity. So we take the largest circle, which is outside, which singularity is outside of it, and this formula works here. Yeah, this function, that determines Fourier series in the point z0 equal 1, 4. Of course, we need not calculate derivatives. You can easily to expand this function around 0.14. So you plus this point and minus this point. How to calculate derivatives is not a good idea, because if function is more complicated, it will take a lot of time. How we expand this function in the point 1,4? We write 1 minus z and z minus 1, 4, 1, 4. And then I should write this plus, I should write minus 1, 4, plus minus. So 1 minus 1, 4 is 3, 4. Yeah. Then I take this away. I take this away, so it is 1 divided 3, 4, and here is 1 minus, it is elementary, but it's 1 time, it's good to do, divided by 3/2, 3/4. And now we can expand this by using geometric progression. So, and we will get this, precisely this formula. You know, because here it is simple to also it takes time to calculate these derivatives, but here is more or less my idea is if you have some function and just extract z minus 0 in this function. So as we did here, Okay. Okay, so now I think we finished maybe this Taylor series. We go. Example, yeah, exponent ez. No, it's expanded in the whole plane, and the series converge because n factorial go to infinity, essentially stronger than z in the degree n, yeah? So somewhere in the course of usual analysis, you know that, not z, for example, Rn, n factorial, it go to 0 and go to infinity, and moreover it is go essentially stronger for any a, and it's go essentially quicker than geometric progression. Have you seen usual analysis in comparison how go to infinity a is the degree n and n factorial? So this is much more powerful. So this series converge. This was your exponential series converge for any a. Did you have this? I think you should have somewhere this. No, in any event, if you did not have, you should now believe me, or how is proved. You should take this and an divided by n factorial is in fact a 10 times, and here is 1 and n, and so finally starting with starting for large n, this an it is less or equal than some q, which is less than 1, and then it will be some block of those who are maybe large, but then it would be this q in the degree k. So in this q in the degree k give this convergence. Okay, so now exponent converge, cosinus, sinus. No, maybe there is no difference from real analysis, because what does it mean that this series converge? It means that this series, we can always write this. Zn, for example, Zn divided by n factorial. It is less or equal Zn n factorial. Z, if you take absolute value of Zn, it is in fact, and you can check this, it's Zn. So I use a sheaf, I take Z in the degree n and take absolute value. It is the same as this, no? Because what is absolute value of Z in the degree n? It is Z in the degree n. And absolute value you can check. It has such property. Absolute value AB or module is the product. As for real numbers, for complex numbers you have this. So and this series converge for any lambda which is Z. So it is less than infinity. Okay, so now you are not afraid exponent Z. You don't afraid cosinus Z. You always can expand them. You can always expand them in power series. You are still afraid logarithm. What would be afraid? It is this function. Of course, usual logarithm 1 plus x. You can expand in power series. Do you have some recollection from course of usual analysis? logarithm 1 plus x is equal. I don't remember. But of course you can check somewhere. No, we can derive, we can calculate derivatives. We should calculate derivatives and we can derive. It should be, I think it's 1 minus n divided by n x. Okay, so in any event, this we can expand it. There is no problem. This is not so good because it would be multi-valued function. This function is multi-valued. But of course, it's not easy to work with functions which take many values. And here people just tell that they have some, we can have some realization of this function. For example, when we consider square root of x, we can have this branch of this function in usual course of analysis. But, for example, f plus x, but we could have even this function, minus x. In the same way, for complex functions, we will have different branches. We will have different branches. You can have one, another, and if there are many values, for example, set in the degree n, it will have n branches and different. And what is, maybe I would approach this, maybe not. What is the main essence of this course? How to unify these branches? Because typically, how we represent graphically this function? We represent it as graph. For example, x, this is square root of x as graph. But here, if it has many values, we cannot make graph. So it would be so-called Riemann surface. It would be very complex surface in three-dimensional space. Maybe we will approach this or not. Okay, in any event, exponent and so all these simple functions are fine, and we can continue. Sinus and so on. Now we go to singular functions. We want to expand function which has, for example, pole in the point 0, 1, in the point 0. Yeah. So we take, because here is a pole, we should again make the same machinery. We should write the contour, which is not contain this pole. It's typically done in this way. This picture was many times. Here is singularity, and we write the contour such that function is analytic inside it. Then the integral is 0. So, and you see, if we take counterclockwise direction, when we go here, it would be clockwise. So this you should understand why this up contour, this out contour, and in contour, they always have different orientation. Because it's come from this picture. In this picture, this was one contour, and this contour was counterclockwise. So we go counterclockwise down, and here it becomes clockwise, and then again counterclockwise. So here, if we then close this hole, this gap, it would be clockwise. So direction of out contour and in contour, they're different. Yeah, so we now do the same. So we can, because function f is analytic here inside. For this contour C, we get this formula. As above. And then we do the same as we did always. We try to disappear this gap. So they go one to another. Finally, they would be jointly, and one go down, another go up, this disappear. So finally, our connected contour would be disconnect in two different contours, inside and outside. And as usual, we write now in this way. So one integral is out contour, another integral is with respect to in contour. And now we, both integrals for out and in, we make with this parameterization. And what we now do, we consider two cases. This case when this delta is less than W minus Z0, W minus Z0. Here we can expand in this way. So if we have this, if we have this, delta is less than W minus Z0, we want again apply geometric progression. So we want that it would converge. So this should be less than 1. So this is for outer contour, as was before. For outer contour, for this one, it is the same as was before. We use this geometric progression, but now we go to inner contour. So the contour which is inside. In the contour which is inside, we have inequality in another direction. So on the big contour, we have this. On the small contour, we have this. Here we cannot write in this way, delta divided by this, because it would be larger than 1. So we do other way around. We write in this way, W minus 0 divided by delta. So now delta on the small contour is in denominator, And now finally we get this formula. That our Fz is equal, that we get two series. One is this one, and the second is this one. So in the first series, it is more or less as it was before. This Z minus Z0 in the degree n. Z minus Z0 in the degree n. And this contour, this is internal, this distance is different. The Z minus Z0 is in denominator. Okay. Now we change summation. So we want to have the same delta in the degree n in both series. But now sum is going from minus infinity to minus 1. In this integral, we change n to minus n plus 1. So now we get this. We want to write as a series with respect to Z minus Z0, but some degrees would be positive as here. This is usual Taylor series. But there is something additional, which was not before, because of the pole, So we get this, and finally we get this, and finally we write this as one series. So this is theorem. So as mathematician, you should do this. If function has a pole in the point Z0, then it is expanded in such series which has not only positive degrees. So without pole, it would be only from 0 to infinity. But here is singularity. Then they appear negative degrees, and this formula is more or less as was before. This series is not more called Taylor series. It is called the Laurent series. And these coefficients in this series are equal to these integrals. What is special here? Before, for Taylor series, for non-negative n, these coefficients were these derivatives, as in Taylor series. But now our function has singularity. All our previous reasons are not valid. We have only this formula for these coefficients. So coefficients are given by these integrals. Before, for analytic function, these integrals were equal to these coefficients in Taylor series. Now it is not the case. So now we have this formula. More or less, this is final theorem. And this series called Laurent series. Laurent series representation of function which is singular in the point Z0. So if function has singularity in the point Z0, it can be represented. It is very similar to Taylor series, but they are negative degrees as well. And coefficients are not derivatives even for positive. They are given by these integrals. So this is enough for today. I shall send you also exercises. And if you will have problems with some exercises, write me to my usual email. And we will take some time on Monday to think to this, to these exercises. Okay, so this is enough for today. Yeah, thank you. So we stop share and we stop recording.